What are we dealing with here? Just in case. Yeah.
So, the concept behind 8 and 9 on the homework. Like the acceleration of an electron, I think.
Okay. But it's a specific homework question?
Yeah, just like the concept, like how, what I do, like go about doing it.
Yeah, okay. Remind me what the question is. Yeah, sorry, I don't have one. I mean, I'll look at a question and okay, yeah, but I don't know what number it is or anything like that. Or if you can give me a general idea, like it's not the charge flying between the two plates, that's like 11 or 12.
That's kind of both of them I've been struggling with.
But while Isaiah's pulling that up, other questions? We're back to Isaiah.
It's like an electron moving so the speed is traveling parallel to an electric field.
Yeah, it's exactly this
Like
one.
both of these have been struggling with.
Okay, well, okay, so the first question is, so either of these questions, they kind of have the same basic starting point. It's an electron traveling through an electric field. Now, first of all, please bear in mind, I don't say anything about how the electric field is produced. Okay? I'm assuming that there is some arrangement of source charges somewhere that produces this electric field. Okay? I don't care about that. I mean, we start off with, okay, here's this electric field. Okay? And there's a key phrase, it's both, okay, so it's both 8 and 9 at the same starting spot, essentially. The key phrase is that the electric field is uniform. Or it uses some sort of, maybe it says uniform. Or if you want to take out that word uniform, you can exchange it for the electric field is constant. You could say uniform, or you could exchange that with the word constant. Okay? So the electric field is constant. That's kind of the starting point. Well, if the electric field is constant, what can you tell me about the force exerted on the electron by the electric field? If the electric field is constant, what can you tell me about the force exerted on the electron by the electric field? Or if we want, okay, so I could back up. If I could find my little doodad, there we go. Let's try this instead. If I go back to this ugly mess, right? How do I find the force acting on my system if I know the electric field due to the source charges? Yeah. How do I find the force acting on my system, the electron, due to the electric field set up by, some unspecified charges elsewhere?
Multiplied by the point charge.
Multiplied by the point charge. You remember the right-hand side of this, the idea is that the right-hand side of this indicates kind of the influence of these source charges. And the left-hand side here is supposed to be indicative of the interaction between those source charges and the thing that you're considering to be your system. So over here, sources properties set up by these source charges, interactions with your system. So if I know the electric field due to the source charges, I can multiply by the charge of the system to find the interaction, the force that those source charges exert on my system. So if the electric field is constant, what can you tell me about the force that that electric field exerts on my system? It is constant. The electric field is constant. The interaction between the electron and the electric field is also constant. Right? Because the interaction is, well, the charge of the electron is constant. The electric field is constant, therefore the force must be constant. Well, okay, the force is constant. What can you tell me about the acceleration of the electron? Also constant. Quick, what physical law would tell you that? What physical law would allow you to say the force is constant, therefore the acceleration is constant? Newton's second law. Right? If the Newton's second law tells you, hey, if the force acting on your system is constant, then your acceleration is constant. Small byline, assuming your mass is constant. And so, like, rocket ships are out. Don't try Newton's second law with rocket ships. Don't try F equals ma with rocket ships. That might be a better way to say it. Right. The F equals ma assumes that the mass of your system stays constant. There's a more general equation for Newton's second law, which I think you saw. It's just a change in momentum over unit time. Did you guys talk about impulse? Okay, impulse. The impulse equation is essentially the more generic version of Newton's second law. Anyway, sorry, brief byline. Okay, so the electric field is constant. That tells us that the force acting on the electron is constant. That tells us the acceleration of the electron is constant. And now a light bulb should be going off in your head. Because if the acceleration is constant,
Use the UAM equations,
UAM.
uniformly accelerated motion.
Oh, yes. In other words, you can, if your acceleration is constant, you can use the equations that are associated with constant acceleration. Now, I've never heard them called UAMs. More often, and your book calls it this, they calls it kinematics. Right? Don't forget those kinematic equations that you covered first and second chapter back in 161. Those are only a very small subset of possible equations. Those equations come from constant acceleration. In fact, you could start with Newton's second law, assume constant acceleration, and derive the kinematic equations. So, electric field is constant, therefore the force is constant. The force is constant, therefore the acceleration is constant. The acceleration is constant, therefore I can use the kinematic equations. Now, question 8. Okay, having that, do I have a blank? Man, okay, blah, blah, blah. Okay, blank slide here. So now question 8 basically has set up, you have an electron. I'll put it moving to the right. So I'll put a velocity in here. And it says that the electron is moving in a uniform electric field. And eventually it slows down, stops, and goes the other way. Which direction is the electric field? If you know that the electron slows, stops, and starts moving the opposite direction, that's enough information to know which direction the electric field is here. Which way is it? Yeah, and this is why I ask. We have to be careful. Which direction is the force?
Yeah.
The opposite way, right? If the electron is slowing down, that means the direction of its velocity is opposite that of the force acting on the electron. So I've drawn the velocity going to the right. That means that the force of the electric field on the electron must be going to the left. Right? So we'll start, okay, so this means that the force acting on the electron must be going to the left. And now here's where we have to be careful, because I didn't ask you about the force. I asked you about the electric field. And how can I relate the electric field to the force?
By the charge of the electron.
By the charge of the electron. The force is given by the charge of my system times the electric field. Okay, that would have been better. I don't know why, I whipped my head around and all of a sudden it's like, I just got dizzy for a second. My inner ear must be like really off. Something. Yeah.
What's the unit of measure of magnitude that says NC to the negative first? Like, I don't understand that unit of measure is.
Sorry, is this enough to get you moving? Okay, let's finish this first, then we can talk about the unit for a second. Yeah. So, okay. We know the direction of the force must be to the left because the electron slows down. And we know that the force is given by the charge of the system times the electric field. So, and this is the one place where you have to be careful now. If the system were a positive charge, right, hypothetical, if the system were a positive charge, what direction would the electric field be? Parallel or anti-parallel to the force? If it were a positive charge, if the system were positive, then the electric field would be parallel or anti-parallel to the force? Parallel. In other words, if the system were positive, then you notice the force and the electric field would be in the same direction, parallel. If the system is a negative charge, the force and the electric field are anti-parallel. That negative sign from the charge of the electron means that the electric field is exactly in the opposite direction as the force. So that's the one place that, yeah, again, and I struggle with that. Like I'm prone to say, oh yeah, number 9 has a figure. Every time I look at the figure, I have to stop for a second because the electric field is pointing down and the electron deflects up. And every time I open up that figure, I have this momentary thing of, oh crap, I drew the figure wrong. Like just a brief instant. Thinking fast. It's thinking fast versus thinking slow. So that instant I see it, I think, crap, I drew it wrong. And then I sit there and think, and I go, no, I did it right. I have to convince myself every time, just for a brief moment. So yeah, the electric field, because the electron is negative, that means that the electric field must be going in the positive, or well, let's call that positive x, just to make our lives easy. So we know the kinematic equations apply. We have an image, a picture of our situation now. So first thing we have to do is find a value of the acceleration. And once we have that, then we can start doing our kinematic equations. Incidentally, that's problem 8. Problem 9, the exact same thing, except instead of one dimension motion, you're moving in 2. Oh, incidentally, for problem 9, it's an electron still moving to the right. It gets deflected upwards. So I'll do this. And the electric field, although I can't draw it very well, the electric field is pointing straight down. Question. What's the acceleration in the horizontal direction? The electric field is pointing straight down. What's the acceleration in the horizontal direction? 0. Good. Huh. If only I've done facetiously, right? This is exactly a projectile motion problem. You have a constant acceleration in the vertical direction. You have 0 acceleration in the horizontal direction. Now, of course, the cause of the acceleration is different. Right here, it's the Coulomb force as versus gravity. But in terms of your approach, you've done these problems, let's see. Chapter 1 is going to be units. So chapter 2 is probably 1D motion. So probably chapter 3 was 2D kinematics. So you can revert back to the stuff that you've developed in chapter 3. Again, bear in mind, you have to tell yourself, convince yourself the acceleration is constant first. You get that, then all of a sudden chapter 3 material opens up. To answer your question, Isaiah, questions on that? Q of the system is the electron that is moving through the field. So I want you to consider the electron to be your system.
So would this be the electric charge, the Coulomb?
Yep, yep, exactly, yep. Any questions on that? Of course, I qualitatively followed through to get to the constant acceleration. You could write down equations and actually quantify it, right? The electric field is constant. Okay, well, I have the value of the electric field. I can find the value of the force. I have the value of the force. I can find the value of the acceleration. I have the acceleration and some other quantities. I can start thinking about kinematics. Isaiah, to answer your other question, you had said something about, hey, I see this unit. What is that? Is that what you were looking at? Mm-hmm. Don't forget the negative exponent. If you don't like that negative exponent, you can move whatever has a negative exponent to the opposite side of the fraction. So if you have a negative exponent, you can move it. In this case, an exponent in the numerator, I can move it down to the denominator. So for whatever reason, the system doesn't like writing this. I think it's programmed in as a Newton per Coulomb, but when it displays it as a Newton times an inverse Coulomb, or a Coulomb to the negative first. So that's all it means, is that take that C and move it to the denominator. And just so we're clear, you say, well, how do I know it's just the C and not the N and the C? Well, first of all, there's no parentheses, right? Don't forget PEMDAS. So you do the exponents before you do the multiplication. And the other way to say it is, capital N is not a prefix for units. Lowercase n, yes. Meters, yes. Capital N isn't a prefix for units. So you go milli, centi, deci, tera, giga, mega, peta, nano, pico, femto. You go through and all of it. There's no capital N. Does that get you rolling, Isaiah? Okay. Yep. Yeah, so a lot of that kinematic stuff. Yeah, well, so you can imagine stuff applies. Oh yeah, sorry, slight byline. Problem 9, when you're shooting the electron through the two plates where there's an electric field. Is this ringing bells? I don't know, I was having a discussion, I forgot to put, I should put a link in the general comments after you finish the problem. That's how your old CRT stuff used to work. Have you, or the CRT, anybody remember the day and age where the televisions took up like an entire table? Like it used to be, you could not put a television on a mantle unless your mantle was like, 3 feet deep.
Well, it used to be like a piece of furniture.
Yeah. Yeah, literally, the TV I remember growing up with was literally about 3/4 the size of this desk in front of you. Okay, and it was black and white, and you had to do this terrible, okay, that's not gonna work. You had to do this terrible thing where you actually had to walk up to the TV and physically turn a dial to get a different station. Oh, it's terrible. Okay. Fortunately, I can't remember what happened. I think lightning struck the house or something like that. And we finally got it, by the time the second TV came in, it was, maybe a third of the size of this thing. You could actually set it on a table. And then you wish you had the old TV, because then at least you didn't have to like go out and buy a table. And anyway, okay. So have you all seen like one of those big, bulky, like why is this box so deep? Why is this thing so big kind of television? Yeah, so, okay, good. I see some nodding. That's good. That technology was called CRT technology. Abbreviation, cathode ray tube. So it's not that, CRT, cathode ray tube. Sorry, this is really hard to look. Yeah. Now you guys are a lot better than I am at this stuff. I never remember anode and cathode. Except now that I think about CRT, I don't think I'll ever get it mixed up now. Cathode is it seriously? Crap, now I'm gonna be forever confused. Cathode is positive, really? Cathode is the positive charge? Oh, nutser. Well, now I'm really confused. I'm gonna have to go back and have a reckoning. Okay, CRTs, cathode ray tubes. What happened was the reason that box is so deep. On the front side, you have a screen, where the image is. Sorry, this is just old technology, but I thought, I asked this homework question and I forgot to tell you why I asked it. Like, it's not like I just made up this thing. It's like, no, this is technology that was used from the 60s to the 2000s. Okay. So what happens? The cathode ray tube, you have a phosphorus screen on one side. Okay. And you say phosphorus coated because what you want is when an electron hits that screen, you want it to give off a flash of light. And so it's the same reason why you put coating in the light bulb. No, that's a different thing. Okay, never mind. But yeah, you want it to, when it hits the screen, you want it to emit a small flash of light. That's number one. Number two, how do you get the electron to different parts of the screen? Because what happens, the cathode ray tube, what happens is you have the screen over here. There's the screen. You have a single source for electrons in the back of the television. But when I form a picture, I need to put flashes of light at different locations on the screen. So how do I get these electrons to different locations on the screen so that I can get flashes of light at different locations? And if I do that really fast, incidentally, that coating, you hit it, you get a bright flash, but it slowly fades. All right. So what happens is that if you hit it fast enough, you can form an entire image on the screen. So how do I direct those electrons to different locations? You already know the answer. You have a moving electron. You want to deflect it upwards so that it hits the top of the screen. You make an electric field. Those CRTs part of those old televisions, you have an electron source, which I thought was the cathode, but apparently it's the anode, so now I'm really confused, so I don't know. Okay. But you have an electron gun, you have a source of electrons in the back of the television. Then you speed up those electrons, generally using an electric field. Okay. So you set up an electric field like this, and you speed them up, then you run it through a couple of regions of electric field, either going, excuse me, that's bad, either going up or down. That will deflect it vertically. And then there'll be another region that's left or right, which will divert it side to side. And the combination of the up and down deflection and the side to side deflection will direct it to different locations on the screen. Now, of course, you can imagine that up-down deflection and the left-right deflection have to happen pretty fast, right? Because what you're doing is you're basically taking excuse me, I'll say an electron machine gun. You're going in the back of the TV, and these electric fields have to adjust so that as you're going in the back of the TV, the electrons are going and they're spreading out all over the screen, right? And then you get your image. So this is that's the old technology from, you know, the 60s until the 2010s or so. And generally the other problem was the bigger the screen, the more deflection that you need for the electrons. And generally that meant the deeper the television had to be. Because what happens, you need to give the electrons more space to fly vertically to the right position. So it used to be that, you know, the larger the screen, the deeper the television had to be, which kind of limited how big you could make a TV screen. And yeah, I think by the time when I bought my first TV in undergraduate, I think it was about that deep. And it had like I think it had a 24-inch screen, and it was flat. So the actual glass used to be curved just slightly. It was true like flat glass on the front. And then of course then LEDs came in, and by 2010 it's like, okay, why are we moving around these furniture-sized boxes? And LED works off a completely different technology, which is why all of a sudden you went from a meter, and within 2 years, 3 years, all of a sudden you're down to a couple inches. Okay. No? Question, I mean, so there's some practicality here. I'm sure that this is, you know, I'm pretty sure I'd have to double check on like the development of mass spectroscopy, but like you could use this as a very crude sorting device for charge to mass ratio, which is why I put that fourth piece in there about you do it for the electron, now do it for the proton. You'll get a different deflection in a different way. And I asked that just because it's a very crude sorting device for particles that you can't do by hand. So I think that's the other kind of fascinating thing about getting to know the electric field and the magnetic field, is it will allow you to start separating things that you can't grab with a tweezer and just, you know, okay, I'm going to take that hydrogen and I'm going to put it over here, and I'm going to take that oxygen and put it over here. And so it gives you a way of doing that, you know, without. No, maybe. So yes, if you're taking, okay. All right, so we have Dr. Phillip and Dr. Phillips. And I know Dr. Phil, so I don't usually call him Dr. Phillip and Dr. Phillips. So I don't really pay attention to last names, but I know that Dr. Phillip, is that right? I think Dr. Phillip doesn't like to be called Dr. Phillips, right? Like, yeah, I get the last name right. So Dr. Phillip, you know, when you hit Dr. Phillip, Dr. Phillips, apostrophe S, not S apostrophe, Dr. Phillips instrumentation class, you'll come back to some of this. Oh, by the way, there's neat ways to actually make sure that you know exactly how fast the electron's traveling. So not only will you get a way of sorting particles, but you'll also get a way of controlling how fast they're moving. And that's, yeah, that's the basis of mass spectroscopy. You'll use it for other things as well, but. All right, that just came back to mind because we talked about it yesterday, and I was like, oh yeah, I should say this to the whole class. So if you ever find a television, you know, you can, one of those old CRTs, you know, pop off the back and you'll find something that looks really complicated, like a little electron machine gun at the backside. Probably not safe to take the cover off and turn it on. My guess is, well, if you take the black plastic cover off, my guess is the little electron machine gun is going to be inside of like a metal box. If you take the metal box off, don't turn it on. Because, I mean, you're probably familiar, like you can get a lot of x-rays and that kind of thing from these devices as well, right? Which scares me. Oh, have you guys looked at, okay. Questions on that? Okay, that was 100% related to, you know, what we're doing in class. Yeah, have you guys ever looked at like the historical photographs in the hallway? Like walking up and down this hallway, for example. I mean, of course you have some of the medical ones like in this hallway, right? But some of the historical ones on this hallway, man, they scare me sometimes. Yeah, look for the one, there's a gentleman, you know, in a suit, student, and he's got like one of those viewfinders to his eyes and he's going like this. Right. It's like one of those like magic eye, or not magic eye, but those little clicky things that you used to look at pictures through, like those stereographic things. Okay, so it looks like it has like one of those stereographic things in front of his face and he's going like this. Every time I walk by, I cringe inside. You know what he's looking at? He's doing an x-ray of his hand. Yeah, so what he's got one of these cathode ray tubes. One of these cathode ray tubes is sitting on the table. He's got the viewfinder because, of course, you can't see x-rays. Okay, but you can, again, set up some sort of like phosphorus screen kind of thing. Can't remember exactly if it's phosphorus or what it is, but that's what's in the viewfinder. And he has his hand there because there's an x-ray source sitting on the table on. He puts his hand between the x-ray source and the viewfinder, so he's looking at an x-ray of his hand. Incidentally, he's not wearing a lead vest or anything, and goodness knows how long he stood there for. That's why you don't take the metal box off and then plug it in, because if you do that, you're probably going to expose yourself to some x-rays. I always find that fascinating. You know, in a shoe store, what you used to do when they first discovered x-rays, one of the nice things about, you know, x-rays that they tried to do. Oh, how well does the shoe fit? So you could literally go into a shoe store, you could put the shoes on, step up to the machine, turn it on, and look and see an x-ray of your feet in the shoes to determine how well they fit. That's kind of a bad idea, right? Are you familiar with this? Yes or no? Like, yeah, like it was the Wild West when x-rays were first discovered. You know, and then you get Watson and Crick, and don't forget Rosalind Franklin, right? Yeah, and then, hey, there's this thing called DNA and X-ray. Yeah, do X-rays cause mutations in DNA, or is it just gamma rays? I can't remember. X-rays do it too? Okay. Yeah, you know, there's this thing about DNA and X-rays are bad for it and blah, 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 blah. Yeah, okay. You know, there used to be a toy in the 50s where you could get weapons-grade uranium?
We had demonstrated that.
Yeah, it's like the most dangerous toy ever. Yeah. Fortunately, they discontinued use. But yeah, you could get weapons-grade uranium for a couple of years. There's still one or two floating around, but they're so dangerous like that. I'm sorry? Yeah, they should start it up again. Okay. Okay, that's all I have to say about that. Some just practicality, some, hey, this is just pie in the sky stuff. This is stuff that does get used. And some fun facts that you can impress your friends with about weapons-grade uranium. Okay, let's get this out of the way because, yeah. Okay. Yeah, so we did some comments last time about, hey, here's the electric field, here's the force. We discussed conservative forces, and essentially the one sentence synopsis is, if you have a conservative force, you can write down an expression for potential energy associated with that conservative force. They said, hey, Coulomb force is a conservative force, so we can write down a potential energy. That's supposed to be this rigmarole. Let me get the background stuff out of the way. So if the force is conservative, you can write down an equation expressing the potential energy. I said, oh yeah, it would be nice if we had an analogy for the electric field. You know, since the Coulomb force is conservative, we made some analogy to the electric field describing the source charges only. And since this relationship exists, it's nice if there were a scalar quantity that we can use to express or to extrapolate the electric field. And indeed we do. We call it the electric potential. And I'll start there. If you're thinking about these topographical maps again, this is the equation that tells you the specific shape of the hill. Okay. So if you have a charge located somewhere and you want to say, well, what exactly is the shape of the hill? That's the expression giving you the shape of the hill. The side of the hill goes like 1 over r. Same thing if you have several charges, several source charges. Each one generates its own, electric potential. The total electric potential at a field point is the sum of the individual contributions. So superposition is still fine. The upshot is you don't have to worry about vectors. This is a scalar quantity. And so you can do the electric potential for each of these source charges and just add them up and be done. You don't have to break into components. You don't have to add by components. You don't have to, find magnitudes and angles and all that kind of stuff. Incidentally, looking at this expression, if I have a negative source charge, the electric potential is negative, right? Below ground level, if you will. It's a valley. If I have a positive source charge, it's a mountain. Same thing applies, yeah, that's right. Notice on the potential energy, okay, by definition, you can have potential energies that are less than 0. And you can have negative potential energies here. That should make some sense. I mean, usually if we're thinking about gravity, say gravity close to the surface of the Earth, we tend to define 0 potential energy at ground, right? At the ground, we tend to say it's the 0 potential energy mark. Is it possible to have negative potential energy? Survey says, yes. What do you have to do? What do you have to do to have negative gravitational potential energy when you're close to the surface of the Earth?
Origin is above original point.
I'm sorry?
The origin is above your original point.
The origin is above your original point. In other words, where we decide to call 0 potential energy is above your head. Now, usually, we think of 0 potential energy as being associated with the floor. So if I want negative gravitational potential energy, dig a hole, right? Go below the ground. Now, the only reason I mention this is don't let the negative potential energy disturb you. Because at the end of the day, the thing that's usually important isn't the potential energy, it is the change in potential energy. And when you're dealing with a change in potential energy, it doesn't matter where you call 0. Right? Whatever you set as 0 potential energy, usually that won't matter when you're dealing with changes. So I just wanted to put that plug in there. If you ever end up with negative potential energies, don't let that disturb you. Okay, usually you're dealing with the change in potential energy. I'll leave it there. Leave it there for right now. Okay, there we go. So, I'll try to be careful. Usually, people will refer to the electric potential, V, as simply the potential. I will try as best I can to say electric potential when I'm talking about V. But please bear in mind, and as you go through the rest of your careers, that is not universally applied. Most people will say potential or potential energy. So when you're dealing with potential, when you hear the term potential, more often than not, you're talking about this expression in the fictitious lower right-hand corner. Well, I guess the right-hand corner is not fictitious, it's the expression that's fictitious right now. But when you hear potential, you're talking about this one. When you hear potential energy, you're talking about the interaction of the source charges with the system. I will try to say electric potential and potential energy. So that's the first one. Of course, the second one I think I've already warned you about. And unfortunately, this is just, there's 26 letters in the alphabet, and for some reason, V seems to be popular. Okay? So we have to be careful because this is where V versus VAB versus delta VA is not to be confused with V or V. So you go, okay, what do I mean here? Okay. So unfortunately, V, we'll start here, I'll say electric potential. Okay? Which is not to be confused with capital V, which can also be volts, the unit. Of course, that shouldn't be confused with VAB, which is what I consider the change in electric potential between two locations, A and B. And I've put in parentheses I can't remember specifically if our book uses it, but if you crack open a different textbook, chances are you might see this notation. I'd say it's about 50-50. Okay? So some books will write delta V, other books might write VAB, referring to the change of potential between the change in potential between field point A and field point B. I'll try to use the delta notation because that's what I think that's a little better in terms of being explicit. But I wanted to put both of those on there. Of course, this should not be confused with V. Generally, we think of V without the vector symbol as being a speed, and V with the vector symbol being the velocity. This is a case where V is not V as versus delta V versus V versus V. So that's a warning, just be careful. When in doubt, step back and ask yourself, which V am I thinking of here? And in particular, usually the one that I think is probably the most often confused is the electric potential versus the change in the electric potential. So just be careful. Questions?
Dr. Robinson, I have a quick question.
All right.
Did you hear me?
I can hear you, Leo. Go.
Oh, you said there was something on the board that was and I kind of missed it. I think probably the sign for potential energy. Is that the U looking thing? Or is that something else?
I'm sorry, the U?
Yeah.
Uh-huh. What? Yeah. Sometimes U is used for potential. Yeah. I'm sorry. Some books will use U for potential energy. And other books might use PE.
Awesome. Thank you.
Yep. Other questions?
Can you say again the difference, or just like repeat the difference between electric potential and potential energy?
Potential energy. Yeah, so the electric potential is just saying something about the sources. Whereas the electric potential energy is giving you something about the interaction of your system with the sources. So similarly, the electric field is something that's established solely by the source charges. The electric potential would be the same way. The electric potential is something that's established only by the source charges. And then if you want to get some sort of interaction, you introduce whatever your system charge is. Is that? Yeah. So the other way to think about it, maybe let me know if this helps. If not, then just completely disregard. One of the things that I remember struggling with learning this stuff or trying to get a handle on it was, we'll go to this electron flying through the electric field. And so what we were just talking about, the electron going through the electric field, what happens to the electron? One of the things that I remember struggling a lot with was thinking, hey, the electron produces its own electric field. Is the electric field external to the electron affected by that electric field? In other words, I would confuse the electric field that my system is producing as versus the electric field being produced by the external sources. Okay. And then I would get a little bit incapacitated because I would say, well, the electron produces its own electric field, so doesn't that change the constant electric field through which it's traveling? And then the constant electric field is no longer constant because the electron's moving, and how do I do this problem? So and that's partially why I emphasize the system versus surroundings. Nowadays, I would say, no, I don't need to worry about the electric field of the electron because it's my system. It can't exert a force on itself. So I don't need to worry about that. The electric field I need to worry about is the one of the source charges, the thing external to my system. So I don't know if that helps or not. The potential is the same way. I don't have to worry about the electric potential of the electron. What I need to worry about is the electric potential of everything external to it, the sources. I don't know if that helps or not. But, yeah. Yeah, don't exert a force on yourself. Or a net force on yourself. I guess I should say it that way. You can exert a force on yourself, right? Unfortunately, I can't do this, and I don't know. Maybe that sounds like another Christopher Nolan movie, right? Where you could exert a net force on yourself, so you could do this and go flying across the room, right?
So if you were to have, like, for example, if you were in a sailboat and you were to use a leaf blower, like, while the sailboat would move.
You wouldn't move. Mm-hmm. Yeah, because the issue is the leaf blower pushes on the sail.
It also pushes back on.
But it also, yeah, through the interactions of your feet with the boat, it also pushes back on the boat. Yeah. No, I mean, of course, there's small ways around this. Like if I angle the sail and then I throw the leaf blower on it, then some of that air is actually going, like you're not keeping the systems contained. You're
like run back with the leaf blower, like kind of like how you roll in the water. You could run back with it, turn it off, and come back up.
Let's see, would that work? Yeah, but it's because the air, when it hits the sail, doesn't like bounce straight back. It's going to go off to the side and into the surroundings. You're basically changing the mass of the boat by taking these air particles and shooting them off. Yeah. So ideally, if you put it like all self-contained, yeah, you wouldn't go anywhere. Yep. Okay. So I'll re-emphasize, if you look at the electric potential, this is conveying the exact same information as the electric field. So again, if that, it only pertains to the sources. The electric field is the sources. The electric potential will only be the sources, the source charges, because it conveys the exact same information. And then we go back and we look at it, right? We say, based on the map of the electric potential, how many charges are present? What say you? Two. I agree. Not a trick question. Okay, I agree, two. How do you know there's two? I mean, what do you notice about this plot that tells you there's two?
Just the way the map's like drawn, because there's two different sources there.
Yeah, and how do you know that those are sources? What specifically, I mean, aside from the fact there's a big block, like a big white circle there, but how could you use the map, if you will, the topographical map of the electric potential to know that there are two charges? Yeah, close to each other, they get further apart. You notice that because those topographical lines are closer together, this must be a really high peak or valley. This must be a really high peak or valley. Well, where do high peaks or valleys occur? That's where the charges are. Yep. And we're done. All of the stuff that you can use for topographical maps now applies. The only thing that changes is the terminology. So you won't see this called a topographical map. It's a map of the electric potential. Second of all, these lines no longer represent a constant elevation. These lines represent a constant electric potential. So for each line you see there, it's a value of say 10 volts. Just making up a number. Now, most of the time you won't see it called constant potential. You will see it called an equipotential, equal. So each of these lines is called an equipotential. Man, if I could actually spell. Well, I guess I can. I realized I didn't. Equipotential. Say, I'll put in here either line, or maybe you could, sometimes you'll hear it called an equipotential surface. Surface. Man, that looks like a U and it should be an A. So if you're just looking at kind of this two-dimensional map, each of these lines is an equipotential line. Or if you end up thinking about three-dimensional objects, it would be an equipotential surface. Good so far?
So do we know by those maps whether or not the source, or whether the source is like positive or negative, or do we not have enough?
Yeah, I would have to give you a little bit more information. How this is trying to convey it is that it's trying to convey that this is one and this one's the other. You notice the blue is versus the orange. But yeah, we could just do something like this, and then you're wholly set to go. And I believe I'll have to double check. Like if you click on when I post it, that'll be clickable, but you can click on it and actually move it around and see how the equipotential how it will look different as you put them at different locations. And I'll have to double check, but I believe it'll also allow you to change the charge values. So if you have like a dipole arrangement, or if you make one really positive, one's not, like slightly negative or something, I think you can make them both positive, et cetera, et cetera. I'll have to double check that though. Yeah. Other questions? know I have a series of these, so I think I'll go through the series of questions first, and then I'll ask you the one that popped in my head. Otherwise, I'll just get distracted. Yeah. No picture, no picture. Oh, I did, okay. So sometimes this is, oh yeah, this kind of figure is sometimes referred to as a contour map. Have you heard that before? You might run into it, so if you're doing like MATLAB with statistics or something, you might run into it, but this is called a contour plot. Contour plot, or a contour map. So, you know, you have some, say you're looking at, I'm trying to come up with a good chemistry example. I'm failing miserably, but let's say you have like a surface that's being like an oven, like an electric range or something, and you want to know what the temperature is at every location on the top of the oven. Okay, you could do something like a contour map, and the lines would represent lines of constant temperature. Something like that. You know, say you're designing an oven, you want to make sure that you're getting even heating. So one way you could check that is, you know, you could see, well, how many contours are actually on this map. You know, more contours mean more uneven heating in your oven. Two-dimensional surface, and then you could say, well, look, that spot's too cold, this spot's too hot. Let's try to manufacture to get better. Okay. Or it could be something like a contour. Oh, okay, cell phone. You could do like a contour map of the cell phone. You turn on a white screen and you want to make sure that all the pixels are roughly the same intensity. All right, so like let's say you're developing a cell phone screen, you turn them all on, you make a measurement of the intensity, you could produce a contour map to show where parts of the screen are too dim and other parts are too bright. And then you could, for maybe some manufacturing reason, right? Like there's glue right here and that's causing those pixels to be dimmer than they should be. Or I don't know, anybody getting, shoot, what's it called, like that pinkish color on your phone? I can't remember what it's called, but like after a while, like some of the LEDs start kind of going out, and so it gives a slight pink hue to parts of the phone. Tends to be on the top because that's where that status bar is. So those pixels tend to be the same color for long periods of time. So they tend to start losing some brightness and some coloration. Anyway, this is called a contour plot. That's a top-down view. If you kind of like to see the three-dimensional kind of stuff, you can also do something that's slightly askew. And then you get an idea about which one's the positive and which one's the negative. Okay. So this is more fancy, but not necessarily more informative. Okay. It looks pretty, but it's not necessarily conveying any more information that you don't already know. So, okay, yeah, like I said, they provide the exact same sort of information. So I meant for the charges not to be present, but you could set up something like 4 charges and look at the electric field lines, or you could set up 4 charges and look at the equipotential lines. And oh yeah, how do I get the electric field from the electric potential? What do I look at again? I mean, if I gave you this, how could you determine the electric field map? Or an analogous question. If I gave you a topographical map, how would you tell me about the direction that the force would be if I drop a ball on the side of the hill? How do you read a topographical map, in other words?
Look at the peaks and valleys.
You look at the peaks and valleys, okay? That'll tell you direction that things roll. Okay? How do I draw the line, the length of the lines? What do I need to look at? How close together, right? Lines that are closer together means a steeper slope. Steeper slope means I should draw a longer line for the force. That's if I'm doing topographical maps. Here, the same idea. Lines that are closer together, equipotential lines that are closer together means a steeper slope. And a steeper slope means a stronger electric field. And then, yeah, peaks and valleys. So, okay, well, I've got a peak. My lines are close together. Okay, well, draw a large arrow that way. But, okay, out here, you notice the lines are further apart. Okay, well, I'll draw a smaller arrow. And then you can go through and start mapping it out. And I realized suddenly, to my dismay, incidentally, I posted this on Moodle, so you can just go into Moodle and click charges and drop them around and kind of visualize the electric field. I realize a problem right now with this image. What do you notice about that image? What can you tell me about the strength of the what? All are the same magnitude. This map, this image, and the same thing with the little thing that's on Moodle, because this is just a screenshot of it. It's drawing all of the arrows the same value. It's just trying to give you a sense of the direction of the electric field. Right? If you want to know an actual value, like the appropriate length arrow, I think if you notice on this, again on Moodle, it'll have one for positive, so it'll let you drop positive charges. It'll let you drop negative charges, so you can, do whatever you want. And then there will be one that's called a sensor. I think it's a sensor. And if you drop a sensor in at a location, it will draw the electric field appropriately scaled. Part of the reason that they do that, for presentation purposes, when you get way out here, if you do the electric field lines scaled, you won't be able to visually see them. So then it's hard to tell, okay, well, what direction is the field actually going? So they scale them all to be the same. Similarly, if you go in here, the electric field line will be so large that it'll like shoot off the screen. And so they scale them just to give you a sense of which direction they're pointing. So I'll play around with that, and it's embedded straight in Moodle, so you don't have to go to a separate site. You can actually just click and drag the charges right on the Moodle page. Yeah, so let's remember that the slope of the equipotential lines is related to the magnitude of the electric field. And yeah, we can use these peaks and valleys to kind of visually see what direction things are going to be pointing. Also for completeness, two charges of the same value or magnitude but opposite signs. What do we call that again? A dipole. Four charges, same magnitude and opposite signs. Like in this arrangement. Quadrupole. Quadrupole. And yes, you have the same thing in octupole. 8 charges, 4 of each sign, same magnitude, arranged in an alternating pattern around the circle, et cetera, et cetera. Yeah, to be continued. So this would be called a quadrupole arrangement. Elevations, yeah, I put elevations in there. Okay, so you could do things like this. Here's a dipole arrangement. Where's the electric field the highest? I've given you 5 different field points. Go ahead, talk with your neighbor. Where's the electric field the largest? I gave away the answer, but I'll let you know. In fact, you could probably rank them. Yeah, go ahead and rank them according to the magnitude of the electric field. If you say, okay, I already know which one's the largest, okay, go ahead and rank according to the magnitude of the electric field. Yeah, it's even better. Oh, I missed my hydration for the last class. Thank goodness it wasn't a gallon. No? Hey, you gotta stay hydrated. Yeah. We're going for a run later, right? I don't know, are you a runner? Swimmer? Backpacker?
What, no, it's
On the, yeah,
it's.
which letter, sorry, which letter?
In fact, you could probably give directions too.
No, I know that too, I was like, oh.
Okay, let's go for a ranking. In terms of magnitudes. Is that enough time? Are you okay? You got the idea?
Yeah.
Okay. In terms of magnitudes. Largest magnitude. Which location? Which field point location? E. How do you know?
Lines are closest together.
The lines are closest together, right? That's it. Largest magnitude, lines closer together, steepest slope. Okay, so I would say, yeah, E. What's next? Which one has the next largest magnitude? B and C. Yeah, I agree. And then the next largest.
B and C equal and A and B equal.
Yeah. Yep. Yeah. So, okay, so you got, and similarly, you can get an idea about direction. What's the direction of the electric field at field point, I don't know, B? Up towards the top of the screen, right? You can imagine if I dropped a positive charge at location B, which way is it going to roll? And it's going to roll downhill away from the positive charge. So it'll be towards the top of the screen. How about right here at C? Which direction is the electric field pointing at location C? Yeah. I see some of you saying up. What say the rest of you? Good, right? Again, if I drop the positive test charge here, I just want to make sure you didn't say down, right? Yeah, if I drop a positive test charge here, well, it's going to roll downhill. So this is the downhill side, so it's going to, good. Different question for you. Which of these equipotentials is 0 volts? Go ahead, talk to your neighbor, see if you can figure that one out. So I don't have these labeled. I don't have any numbers here. But you should be able to tell me which of these equipotentials is 0 volts. Which one represents an elevation of 0? Oh, are we? Oh, shoot, we're to be continued. Right, debate on that, right? As you're eating lunch, you can argue about it. Which of these equipotential lines is 0? 0 volts represents ground, if you will. Right, because we talk about equipotential distance above ground, 0 point. Which one is the 0 point? Okay. Thanks. Sorry I went over a minute. I apologize. Have a good Wednesday.